Welcome back to the deep dive. I want you to visualize that building. You've probably seen one. It's probably windowless, sitting quietly down an alley, just humming with unseen activity. That's your local telecommunication equipment room. For decades, it was just, the definition of passive infrastructure, a simple hub. Its job was just to make sure your phone calls went through and your internet worked. We are going inside that building today because a quiet revolution is underway. And it's fundamentally changing how our physical world and the digital world connect. The core idea here is that this quiet signal transfer station is slowly growing a thinking brain. Our mission for this deep dive is to trace that evolution, understand the specific pressures that caused it, and define what this new decentralized intelligence really means for you.
It really is a systemic evolution, not just an upgrade. I mean, think about the contrast. The old network was a linear, predictable pipeline, almost like a logistics service, right? Designed only to move sealed packages from point A to point B. The future network is completely different. We're moving toward a decentralized, autonomous, complex system. So imagine having hundreds of highly capable, intelligent workshops all throughout your city, ready to instantly process information right where it's needed.
That's a huge shift, and that's the magnitude of the change we need to grasp. So let's start by looking backward to understand just how simple, how rigid the old system really was before the modern era demanded that it start to think. If you strip away all the complexity, the traditional telecom network was built on basically one principle: highly facial transmission. It was a digital pipeline.
Exactly.
What you put in, you got out. No intelligence, no changes, just reliable transfer.
And that structure created what we'd call a classic top-down simple system. Everything was centrally controlled. It obeyed commands from a core network. This made it incredibly stable, very easy to manage. But that stability came at the cost of being, very rigid. The system's fundamental flaw, looking back, was that it was totally unaware of the contents of the packages it was moving.
We had no idea.
None. It was a utility, not a participant in the conversation.
So those local equipment rooms we talked about, they were just passive execution nodes. They didn't need to think. Their only directive was to pass traffic along.
That's it.
They were just dependable postmen delivering sealed envelopes as fast as possible.
And, for a long time, that design worked perfectly. For basic data, email, loading web pages, downloading a file, it was fine. But it set the stage for a critical failure point when a new force, a new kind of demand arrived that required immediate local computation. The old architecture it couldn't handle it.
Okay, so what was the breaking point? It wasn't just more volume, right? The network is always handling more volume.
No, it wasn't volume.
The fundamental change came when the demand shifted from simple data transfer to instantaneous AI generation. We stopped asking the network to just deliver a letter. We started asking it to instantly write a poem or generate a complex image.
And the crucial bottleneck there is one word: latency. If you ask an advanced AI model a question, you need an immediate interactive response. In the old model, that request had to travel all the way from your phone through that passive local node across the whole country to a massive data center.
Wait for its turn in line.
Wait for its turn, get the computation, and then travel all the way back.
I remember trying one of those cloud gaming services years ago. The promise was amazing, but the lag, that huge latency, made the whole thing just unusable. It sounds like AI interaction faces the exact same problem, maybe even worse.
Exactly the same problem, magnified. That lag is completely unacceptable for real-time interaction. The network is now required not just to send the question, but to immediately generate the answer locally.
Right there.
Right beside the user. And that demand for timeliness, for local intelligence, it just paralyzes a centralized system that's built to report everything back to the core.
This makes us realize we have to differentiate between the two main types of AI work because they need totally different network designs, don't they?
Precisely. First, there's training. This is the deep, power-intensive, time-consuming work. It's like building a continent-sized library from scratch. This needs thousands of super powerful chips, and it's done remotely in huge data centers. The old cloud model is perfect for that.
But the immediate bottleneck, the thing that's forcing this local evolution, is the second type of work. Inference, which is the rapid application of that knowledge you already built. It's using the library to answer a question in real time.
And that has to be fast.
It has to be fast, low latency, and local. And if the central system can't do that, it has to evolve.
So the only way to solve this is for the system to kind of self-evolve. It has no choice. It has to convert those passive package transferring nodes into intelligent workshops, into Autonomous computational cores ready to think on the spot.
So if local intelligence is the answer, what kind of hardware actually fixes this latency problem? We know the local node can't fit one of those giant S100 chips used for training. They need too much power, too much space.
And that's the genius of this transformation. They don't need general-purpose training power. They need specialized, efficient inference power. They require the L40S GPUs.
Okay.
And the difference is crucial. It's why this whole thing works economically.
Tell us a bit more about that technical difference. What makes the L40S so good for the edge, where power and cooling are real constraints?
Well, the massive S100 chips are optimized for what we call floating point operations. Think of it as the really precise math needed for training models over weeks or months. The L40S, on the other hand, is optimized for highly efficient integer operations. It means it can rapidly apply existing knowledge, the inference step at way lower power consumption and heat.
So it's a specialist.
It's a specialist. We're sending a knowledgeable, fast-reacting master craftsman to every community, not trying to build the central library on every street corner.
But hold on, this sounds incredibly expensive and complicated. We're talking about retrofitting thousands of these buildings. If you suddenly dedicate half your space and your power budget to computation, what does that do to the cost? Doesn't that create a management nightmare?
That is the central operational challenge, and it's why the investment is so huge. The resource shift is startling, where 100% of a local node's resources were for transmission. Now, up to 50% of the total capacity has to be dedicated to powering and cooling this specialized AI core.
50%, that's a staggering redirection of resources.
It is. This transition completely changes the function of the building. It goes from being a postman to a local ideator, a thinker. And of course, if you're growing a superbrain, the body supporting it has to adapt too.
Right, makes sense. If a person grows a superbrain, the circulatory nervous systems have to keep up. So what are those supporting upgrades? What else needs to be done?
Well, the first and most obvious is heat dissipation, cooling systems. These new inference chips, even though they're efficient, generate way more heat than old routing gear. So you need industrial-grade cooling.
Yep.
Second, you need lightning-fast internal data pathways. That's where the DPU comes in, the data processing unit.
We hear DPU mentioned a lot. How is that different from just a standard network card?
A DPU is like a specialized traffic controller for data. It's designed to offload a lot of the networking and security tasks from the main computer. So when the AI core needs to pull a ton of knowledge from local storage, the DPU makes sure that data flows without creating a bottleneck. It's all about minimizing that latency.
Got it.
And finally, you need that ultra-high-speed storage flash memory so the brain can retrieve knowledge almost instantly. Those three things, cooling, DPU, and storage, are the systems that let the local brain actually function.
Okay, so we followed the story of just one of these rooms transforming. Now let's pull the camera back. Imagine this happening at scale. Thousands of these nodes across the city, all waking up at the same time with these new capabilities.
And that is the real functional definition of edge computing. It represents this critical evolution from a rigid central hierarchy to a truly decentralized, distributed, intelligent network. Intelligence is no longer some remote thing stuck in the cloud.
Right.
It's now woven into the physical fabric of the city, creating this responsive nervous system.
So what does this decentralized intelligence actually mean for the user? Why should I care that the little building down my street just got an L40S brain?
The benefits are pretty substantial and immediate. First, you get near zero latency, real-time interactive experiences. This is absolutely essential for things like industrial automation or, really complex interactive AI chatbots that don't make you wait.
The end of laggy conversations.
Hopefully. Second, and this is a huge deal for businesses and users, is privacy and security. Sensitive data, think medical scans, factory secrets, financial records, can now be processed locally. It never has to be exposed to the public internet or sent to a central cloud. The data stays where you are.
That security benefit alone feels like it justifies a lot of this complexity.
Absolutely.
Yeah.
And on top of that, it leads to smarter, more personalized services. This localized, real-time intelligence is perfect for tasks like dynamic traffic management or optimizing a local power grid. The system can react instantly to what's happening on the ground without waiting for orders from headquarters.
Okay, let's switch gears to the economics. The whole traditional telecom model was just selling bandwidth, right? Selling the capacity of the pipe, like a shipping company charging by weight. But now these thousands of intelligent workshops, they're creating a totally new, highly valuable product.
They're selling brain power.
Yeah.
Computational capacity, right at the point of access.
Yeah.
The value shifts from moving the package to providing the ability to think about the package locally.
So the business model has to shift from selling the pipeline to, well, renting the brain. And this has led to some really interesting and flexible new commercial models.
The market's responded with a few different tiers. The first is long-term leasing of a small guaranteed slice of that local brain. Imagine a city's traffic planning system that needs consistent low-level processing 24/7. That's like renting a small, dedicated studio apartment inside the facility.
And the second model would be for those, peak demand moments, the bursts of computation.
Exactly. That's the time-sharing concept. It's like a resort membership card. A local university or a small business might only need massive compute power for a few hours a week. They can rotate their use, sharing the resources efficiently.
And then, of course, the biggest customers who need intense but still local processing.
They can just rent the entire computing power of a local node for a set period. Think of a movie studio that needs to render visual effects locally to keep their footage secure. Or a factory running real-time quality control algorithms on hundreds of sensors.
This creates a completely new service menu for these companies. They're not just selling internet anymore.
Correct. Their menu now includes pure compute capability, just the brain power. They can offer specialized AI model services with functions pre-installed. But their most powerful and unique offer is the combination package. Their core strength, the fast and stable network, plus guaranteed local compute capacity right at the edge.
And despite the huge capital investment here, the cooling, the DPUs, the chips, there must be a lot of confidence in this new value. I think we saw the investment is estimated to be paid back in under 4 years.
And that rapid return on investment tells you everything. It shows just how desperate the market is for low latency intelligence. It confirms that the economic value created by this decentralized computation far outweighs the operational cost and complexity that, as you rightly pointed out, is a major challenge. The market needs this evolution.
So let's bring this all home and define what this transformation ultimately means for you, the listener. It's a structural decentralization, yes, but it's more than that. It's a genuine democratization of intelligence.
I think that's the perfect way to phrase it. Intelligence, which was once this remote, specialized thing, is becoming fundamental infrastructure. It's being woven into the fabric of our world, available everywhere like water and electricity, just waiting to be used. And if we conclude this deep dive from the perspective of complexity science, we see something profound happening. When thousands of these previously simple, passive nodes suddenly become autonomous, intelligent entities, capable of thinking, communicating, and collaborating, they stop being a simple system. They coalesce into a single, massive, complex system.
The complex system where the whole is much, much greater than the sum of its individual parts.
Precisely. And this is the provocative thought we want to leave you with. What new capabilities, what entirely new forms of service, what efficiencies that we can't even imagine yet will ultimately emerge from this massive, interconnected thinking complex system? This quiet evolution starting in that overlooked room down your alley is really only just beginning.
Thank you for diving deep with us into the brain of the network.
We look forward to the next complex system we can analyze together.